Welcome to the fourth ICP of the semester. In this ICP, we are tuning a neural network. So first we need to import our dependencies, set our seed for reproducibility, and here we are getting our training set. So the CIFAR10 training set is uh, pretty easy to load in. It's already split into training and testing data. So we can kind of visualize that data. We have 50,000 training images, um, and then 10,000 testing images. So let's first visualize the data. We can do this with matplotlib, and we can kind of see that the images that we get are pretty grainy because they are 32 by 32. Um, and we can see that here. Here we want to get the images in the form of a float because that's what our neural network wants to intake. We are using one-hot encoding in this ICP, so we need to um, transform our labels into a categorical list where uh, it's either 0 if it's not that label or 1 where it is that label. So each image will have a list of 10 um, binary digits for each label. And then here we are just taking our height and width that we got earlier when we displayed the images. This is a direct code snippet from the source code in the tutorial. It's one of the layers of our neural network, and we didn't change anything about this. So finally, we're getting to the tuning of the hyperparameters. We have 10 classes. Um, so we didn't tune anything with the data augmentation layer. That was this layer up here. Um, we did tune the convolutional layers, so we ended up actually quadrupling each of the number of filters. We found that, um, for the cost of computation, this gave us better performance, and then we left the activation functions the same, except for down here. So I believe in the original source code in the tutorial, this function had the activation function of softmax, but we ended up changing that to ReLU and using the softmax activation function at the very last layer, the output layer. And that layer has 10 classes for 10 outputs, 10 neurons, one for each class. We compiled the model. Here we didn't change anything. We're using Atom. We did remove this from logits was true, and that's because the softmax function does not output logits, so we were getting a warning when we had that in there. Here's a summary of the model, and here we are fitting our model, so we changed the model to have 35 epochs and a batch size of 200. So originally we'd found that using a small batch size, like a batch size of 25 or 32, was giving us good learning rate, but it also had a high loss because the variance within each of the batches was high. So by using a larger batch size, we sacrifice learning rate, which means we need to have more epochs, but the variance within each batch is smaller. So that's why we had to go with a higher epoch of 35. Uh, we tested all the way up to 50, but found that uh, there was only a marginal increase after 35 epochs or so. So how did our model do? During testing, we found in this particular run it was 78%, but we can see there's some epochs where uh, we get pretty close to 80%. We found throughout testing we would get you know usually around 80% accuracy. So that's a pretty significant improvement from the original accuracy, which I believe was in the 60s. So here again is a similar a code snippet directly from the source code, plotting our accuracy and loss, and we can see our validation loss follows our training loss pretty closely, and same with the accuracy. So that's a good thing to see. So finally, we're gonna validate with independent images. Just gonna import some dependencies here, some libraries. Here is a load image function that we defined. So basically what this does is it takes a URL from the web and transforms that URL into a 32 by 32 by 3 NumPy array, which we can run through the model. It also uses matplotlib to plot the images um, for visualization. Um, another function we defined was a predict class. So it takes the output of this load image function and runs that through our model.predict right here. And then we are predicting the class based on the output of that model. So using argmax here to get the most probable answer. And it's important to note our model is not deterministic, so if you run this model, you may experience different results. We found that the results were pretty often similar, but sometimes on a particular run, it classified something incorrectly or not. So here's our load image function. So we're importing a URL of a picture of a deer. You can see like this was the original image. This was what it looked like when it's compressed to 32 by 32 by 3. So this was a pretty easy image for the model to display. Um, it's a pretty standard picture of a deer. And we can use predict classes, deer image, and we get deer. So that's a good thing. Our model predicted correctly. Here again, we have an image of a cat and compressed to 32 by 32. It predicted correctly again. We decided to give it a hard image. So we had this picture of two cars, and we kind of just wanted to see what would happen if the model tried to predict this. Um, and we found that it almost always predicted it as a truck. It's probably able to tell that the image had wheels, probably able to tell it had like headlights and things like that. Um, but this was a pretty difficult image for it to predict, and not surprisingly, it got it wrong. Here we did an image of a ship. This one was pretty easy for the image to detect, but just shows that we can use a cartoon image to run through the model, and it'll still predict it right. And finally, we have a frog image, and again, predicted correctly. And that's our ICP.